Okay, good afternoon, everyone. My name is Ruben De Wolf. I work at KU Leuven as a PhD student. I'm currently in my second year, and my research is focused on simulations of plasma physics and nuclear fusion. So the purpose of this talk is to give you a short overview of the state-of-the-art nuclear fusion technologies that are currently available, the future developments of nuclear fusion, and to get to that, I'm also going to discuss the history of nuclear fusion, because I want to give you a concise overview of what exactly were the issues, which issues did we already overcome, and which issues remain. So for this presentation, I'm going to start with explaining the concept of nuclear fusion. Why do we know that it exists? Why is it so good? Then I'm going to talk about confinement, because that is one of the most important aspects of nuclear fusion. Then I'm going to look into the history of nuclear fusion and into the state-of-the-art reactors. So first, a kind of obligatory introduction, I think. We all know that energy production is currently not very well done in the world. So we have a lot of global CO2 emissions, and electricity production is about 25% of our CO2 emissions. So I'm saying 25%, but it's actually more, because in road transport you obviously also have CO2 emissions. But we are going towards electrification, so that means that in the future a lot more of our CO2 output will come from electricity production. So we need to meet these electricity demands in a responsible way. And what does it mean to be responsible? It means that the electricity needs to be sustainable, it needs to be reliable, it needs to be affordable, and it also needs to be safe, of course. So all primary energy sources that we use right now have trade-offs, of course. So I've listed a couple of sources here, and I'm quickly going to go through them. So the first ones are fossil fuels. And when we look at the four aspects that I just talked about, fossil fuels are obviously not sustainable. They are reliable, though. They are very affordable, and they're quite safe. Unless, of course, if you count the millions of people that die every year because of air pollution. Then we have renewables, which obviously suffer from the intermittency problem. They are sustainable and not reliable due to intermittency. They are affordable at this moment. They weren't always affordable, but the price has dropped enormously and will continue to drop for the foreseeable future. Of course, renewables are also quite safe. Then we also have nuclear energy, which is somewhat sustainable, but not completely. It's still a fossil fuel, of course. We can run out of uranium, so sustainability is not really how I would describe nuclear fission. It is reliable, that is why it's a base load, of course. A nuclear power plant can just produce enormous amounts of energies at a steady rate. Affordability, yeah, I've put a red cross there, but at this moment it is affordable. But the problem is, if you want to construct new power plants, that is crazy expensive. So that's why affordability has a red cross there. Nuclear fusion is safe. At this moment it is safe. That's also why it's so expensive to make new power plants, of course. The safety standards are off the charts for nuclear fission. So all primary energy sources have trade-offs, but what if we could find an energy source that does not have trade-offs, that's just good all the way through? And one of the things that might meet those conditions is nuclear fusion, of course. I've put there power of the sun and stars, because all stars in the universe are powered by nuclear fusion. In the core of the sun, for example, we have multiple different types of fusion reactions that occur, and that is what makes the sun burn. So in the center of our sun, we have light elements that are pushed together under enormous pressure and temperatures. And of course, that is a very good reaction to have, because there is a lot of energy that comes out of it. I've given an example here of a fusion reaction where deuterium is fused with tritium, and that produces helium, one neutron, and a lot of energy. So if we were able to captivate that energy, then we can make very efficient power plants. But the problem, of course, is how do we make a sun on our planet? That seems like a very hard thing to do. And it is, because if you look at the temperature in the core of the sun, it's about 15 million degrees Celsius, or Kelvin, not that it matters, but and we have also a pressure of 10 to the power of 16 atmospheric pressure. So that is insane. We can never do that here on Earth. So the way that we try to do it here on Earth is we decrease the pressure, but the trade-off there is that the temperature becomes higher, a factor of about 10 higher, in fact. So that means that in a nuclear fusion reactor, we need temperatures of about 150 million degrees, which is, of course, extremely high and extremely difficult to achieve. But if we're able to do that, then we have kind of an holy grail of energy production, because it is sustainable. We have virtually inexhaustible fuel, because we only need heavy water or deuterium, and we can find that everywhere on the planet. Also, during operation, there is no carbon output. We don't burn anything, we just make helium, a neutron, and energy. So there is no carbon output. Of course, during production, there is a bit of carbon output, but that is, of course, applicable to any energy source. It is quite reliable, because it has an enormous energy output. In fact, if you have one glass of deuterium and you fuse the entire glass into helium with the reaction that I showed, then you can power an average household for 20 years. So one glass of water can power a household for 20 years, which is enormous, of course. The problem is it's quite challenging to maintain a stable plasma, so reliability is something that we try to get in the future, but at this moment it's still quite challenging. Affordability, I've put a question mark there, because at this moment it is too expensive to do, but just with any technology, when the technology matures, prices drop, of course. The main selling point of nuclear fusion, however, is that it is inherently safe. Something like a meltdown in Chernobyl or Fukushima cannot happen, because if anything goes wrong with the plasma, it just ceases to exist. And also, we don't really have radioactive waste. With nuclear fusion, we have a lot of uranium, which has half times of like thousands of years, 10,000 sometimes, which is enormous. But with nuclear fusion, we don't have uranium. So there is no radioactive waste. However, I showed you the reaction a couple of slides ago. There is the production of one neutron, and when that hits the reactor walls, those materials get activated, which makes them slightly radioactive, but they have half-times of about 100 years or so, which is very manageable. So, if nuclear fusion is so great, why don't we have it yet? Of course, the extremely high temperature is a problem. 150 million degrees, there is no material on Earth that can hold such a hot plasma. That's impossible. A second difficulty is very difficult physics. We still don't understand all the physics. We have learned a lot over the last 100 years, but there are still things that we don't understand. As I said, confinement is obviously an issue. And what also makes it difficult is that it's very multidisciplinary. So we have material sciences to withstand enormous temperature, superconducting magnets, which is also relatively new. We need cryocooling, advanced robotics, because we can't work in the reactor when it's radioactive. So there are a lot of different disciplinaries coming together here. So that's why it's very difficult. And in fact, the list goes on. I can talk about the difficulties of nuclear fusion for 5 hours or so, but this is the most important part of why it's difficult. So the first issue that we need to solve is confinement. A plasma has temperatures of 150 million degrees. As I said, there is no material that can hold that. But first I'm going to explain what exactly is a plasma. So when we have solid material, everything, all the atoms just closely bond together so that they can't move. When you heat it up, it becomes a liquid. If you heat it up more, it becomes a gas. And if you then continue to heat up your gas, the atoms will bump into each other so much that they break apart. So you just have an elementary soup of nuclear particles, so protons, neutrons, electrons. So plasmas are characterized by extremely high temperatures, but also by charged particles, and that can definitely help us with confinement. Because if you have just a regular gas or a regular plasma without the presence of a magnetic field, just like a normal gas, everything would just move at random. But since plasma has charged particles, they react kind of special in a magnetic field. As you can see, when there is a magnetic field present, the electrons and all charged particles in general, they kind of gyrate around the magnetic field lines. And of course, we can use that to confine the plasma. If we, for example, have a field line that is just a circle, then the particle will keep gyrating around the circle forever, and it will never leave, in theory, of course. So one important aspect is confinement time. Confinement time is defined by an average time that a particle stays inside of a reactor. We want that to be as high as possible, because as long as the particle is in the reactor, it can undergo fusion. It doesn't make sense to make a reactor with a plasma that just leaves the reactor instantly. We can't do anything with that. So this was already known last century. So I'm going to start with the history of nuclear fusion now. So nuclear fusion was discovered in around 1920 because someone theorized that the sun has nuclear fusion reactions, and that's what makes the sun burn. Of course, we try to replicate that immediately. So 12 years later, the first nuclear fusion reaction was achieved in a lab setting, which was a huge first step in the field, and research into controlled nuclear fusion began. So scientists have been trying to make a reactor for about 100 years now. And of course, the goal of a reactor is, first of all, you need to be able to get to the high temperatures. Second, the confinement time needs to be large enough so that you can have nuclear fusion. And of course, we need more power in than out. Why is that an issue? Because the plasma needs to be heated up. It's not going to do that by itself. And also, when you have a plasma at 150 degrees, million degrees, of course, you need to continue to heat it. So you need to put power in, and then with nuclear fusion you get power out, but of course you want more power out than power in. And that is defined by a Q factor, so when it's larger than 1, that means that we have a net profit of energy. At this point, people thought that we would have nuclear fusion within 20 years. So a commercial reactor would be built within 20 years. So that means around 1950. Of course, right now we're 70 years further and we still don't have a working nuclear reactor. So why is that? Um, I'm now going to go to the history of nuclear fusion for one specific type of reactor, but the truth is there are a lot of different possibilities to do nuclear fusion. They're not all equally great. Some really don't work, and they have been abandoned in research. But at this moment, we have a couple of concepts that we think can really work. And that is, on the right side there, the tokamak, the spherical tokamak. Here, the stellarator family are also very popular. And of course, inertial confinement fusion is also a very active area of research. So as I said, we need to confine the particles. So a basic concept to do that is a magnetic mirror. So we have a tube with a magnetic field in the parallel direction. And when we introduce particles in there, they will gyrate around the magnetic field lines, as I said, and you have basically confined your plasma. Now, obviously, this won't work, because the plasma will just leave the sides of the machine, and well, that is plasma leakage, and that is very bad for your confinement times. What we can do is put the magnetic mirror in a circle, so like in a donut shape. Then the particles can't leave the reactor, and they will remain in there for a longer time. Of course, you can't just make a circle of a magnetic mirror, because that would mean that the coils, the magnetic coils, are more dense in the center than they are at the outer radius of the reactor. So we can't do exactly this, but we can do something similar. And that is how the first devices for nuclear fusion were designed. So basically we have a torus-shaped reactor, which is just a donut-shaped reactor. And we have a central solenoid to introduce a toroidal current in a donut. So that means in the direction of the axis. Now what happens when you have a current? There is a pinch effect. Just like with lightning, you have lightning isn't all over the place. It gets banded together in a central axis. So what happens is when you have a toroidal current in the plasma, a magnetic field is introduced, and it kind of constricts the current together. And if we do that hard enough, then the plasma is compressed so much that we can maybe achieve fusion. And that is the whole point of a pinch device. So the first pinch machines were theorized in 1946. Notice that this is already 10 years later than the first lab experiment, or 15 years later even. Of course, that was with the war, with the Second World War, and also it takes time to build such a machine. So from 1946, we started to make numerous small machines for testing purposes, but the problems with this type of reactor became apparent very quickly. No reactor was able to maintain a plasma for even a very small amount of time. So I've included a picture there on the right. That is a top view of the torus, where a plasma is induced and a toroidal current is running. Now this picture is somewhat misleading, because this only lasted for 300 milliseconds. You can't really talk about a stable operation if it breaks down faster than you can blink. So the plasma immediately breaks down, and various issues were discovered. And one of those issues was kink instability, which is what breaks down the plasma immediately when you try to make it. So you see, when there is a current in a toroidal direction, that is not stable. Just like when you have two electrodes with an electric arc in between them, it won't be a nice line. It's going to move constantly. And that is what happens in the reactor as well. So that is a problem, of course. If we can't maintain a plasma, then we can't have nuclear fusion. So scientists started to think about new ways to induce a plasma and a current and nuclear fusion in general. And that is called the stabilized pinch devices. So we can stabilize the current going in a toroidal direction by making the magnetic field stronger there, because the particles all follow the magnetic field lines. So if you have a stronger magnetic field, then the particles will be confined better. So basically, we're trying to give the plasma a backbone, so some kind of structure that it can sort of hold on to. And that is done by external magnets, and the result is that the field lines are also helical. So they are no longer perfectly circular, but when a particle is on the outside of the donut, the helical magnetic field lines make sure that the particles go to the inside when it moves in a toroidal direction. So that is also good for confinement times, because then the particle will remain in the reactor for a longer time. And again here, we expected nuclear fusion to be 20 years in the future, so in 1960 or something. And that is kind of a running joke in the nuclear fusion sector, that it's always 20 years away, as you will see in the rest of my presentation. So scientists started building these stabilized pinch devices. And in 1953, we had a first large reactor called the Zero Energy Thermonuclear Assembly, or ZERA for short. Construction and design started in 1953, and in 1957 we started to conduct the first experiments. And the results were, well, after a month, the first results were in, and they were great. They were absolutely a lot better than we thought. So strong neutron bursts were detected coming from out of the plasma, which is something that we would expect, because the neutron is one of the products that gets created by nuclear fusion. So if you detect a lot of neutrons, then probably it's nuclear fusion. And the measurements for the temperature indicated that the temperatures were about 5 million degrees Kelvin, which is high, not yet high enough, but for that experiment it was high enough, because it's also a quite small reactor, so they theorized if we just make it bigger, then we get to the correct temperatures. And this was seen as a breakthrough. So again, they thought, okay, in 20 years we have commercial nuclear fusion available. But there was also a lot of skepticism, because when they did the measurements again, they noticed that the temperature was actually only about 100,000 Kelvin, which is not nearly 5 million degrees. And also the neutron bursts were discovered to be not due to nuclear fusion, but due to some type of instabilities that were discovered. So they already discovered the kink instability, which was a macroscopic instability, but now there are microscopic instabilities as well, because there are higher temperatures, you have stronger magnetic fields, and plasmas in magnetic fields are inherently unstable. So zeta failed in the end as a result of limited information, and pinch in general was just discarded as an idea. We don't think it will work. It won't, by the way. We know that for certain right now. But yeah, so there was a lot of pessimism back then, because we thought we almost had it, but then we didn't. However, zeta wasn't immediately retired. We can still use zeta for investigating those newly discovered instabilities. Also turbulence, the measurements for the temperature, that's also very important. In fact, the zeta scientists developed new ways of measuring the temperature in a plasma that is a lot more reliable. So that is one of the main results of zeta. So pinch doesn't work, and better measurements. So then, yeah, we need to look for a new device, because this doesn't work. And so the Soviet Union came up with the tokamak. The tokamak is somewhat similar to the stabilized pinch, except that it has a lot of additional coils to maintain a stable plasma, and the helicality of the field lines was greatly improved, or greatly strengthened. Also, if you have more helical field lines and less toroidal currents, then the kink stability is suppressed, because the kink stability was instability, I mean, was the result of high temperature currents, I mean. So when this instability was suppressed, higher temperatures were possible in the tokamak. And in 1958, the Soviet Union built their first tokamak called Tokamak 1. And they immediately noticed huge radiation losses due to impurities. So impurities are particles that come from the wall or something due to plasma interactions, and they go inside the plasma and they have quite a large effect on the temperature and the confinement times. That being said, they were able to solve that, and very high temperatures were achieved and rather good confinement times. Of course, this machine is still quite small, so it's not good enough to do nuclear fusion, but they thought if you make it bigger, then the problem is solved. So again, nuclear fusion within 20 years. But the problem with the new high temperatures and the good confinement times was that certain effects were no longer negligible. If I ask you to do some calculations on a large vat of gas or something, you're never going to take into account gravity, right? If you're doing a thermodynamic analysis, gravity doesn't matter there. But here it does, because it introduces a very small pressure gradient in the vertical direction, and that is a problem. Not a problem that they couldn't solve, by the way. 10 years later, they introduced their new tokamak. They obviously also made tokamak 2 and tokamak 3, but now they also made tokamak 4, and the results were amazing. So 10 to the power of 7 kelvins, that is 10 million degrees, that is a lot. And also very good confinement times. But of course, we were in the height of the Cold War back then, so the US and the Soviet Union didn't exactly get along. And the US was very skeptical for the results of the Soviet Union. So the Zeta team that developed new ways of reliable measurements for temperature were sent to the Soviet Union to verify the results. But of course, back then we were in the Cold War, so 5 scientists from the US went to the Soviet Union, and in the meantime, it was required that 5 Russian scientists went to America so that they have some kind of a collateral, so that they can't kidnap the scientists. But when the Zeta team arrived there, the results were in fact verified. So the results that were there were correct. And this was a huge leap in the field. So now everyone is very optimistic again, because it was shown that it's possible. So again, nuclear fusion within 20 years. So that means 1990. But of course, that doesn't work because we still don't have nuclear fusion. So at this point, they theorized that there was only one serious problem that remained, and that was the heating. Previously, the plasma was heated by the large toroidal currents, so ohmic losses basically, and that heats up the plasma. But now the toroidal current is a lot less, and also at such high temperatures, the resistivity of the plasma drops, so you can't efficiently heat it anymore. So that was a problem in achieving even higher temperatures, because the temperature now was 10 to the power of 7, we need it to be more. So in the 1970s, the US, the UK, the Soviets, they did a lot of research to make a new reactor. And the US solved the heating problems by introducing a new way of heating, which is called neutral beam injector. The US also theorized that a D-shaped plasma would be better than just a circular plasma. So that is something I will show you in a couple of slides. And in the meantime, the Soviets also discovered superconducting magnets. They were able to produce them, to test them, and they seemed to work. And that was, of course, again, great excitement, because you just combine all the things we just discovered. We put them into one reactor, and there we go. We have nuclear fusion. And that is the goal of the Joint European Torus, which was built in 1982. Now, when this was built, again, new problems were discovered. So no instabilities, plasma disruptions, and in general, the confinement time was just a lot lower than expected. These plasma disruptions, by the way, they were unknown prior to JET, because they are a result of extremely high temperatures. So what does it mean, a plasma disruption? You obviously have very hot plasma, very large currents. The problem is when the plasma touches one of the walls, it just breaks down. But not only that, because there are actually a lot of things that can go wrong there with plasma disruptions. As you know, the currents in such a reactor are extremely high, and when something goes wrong, that current can go haywire. So one of the things that happened was that the current just shot through the reactor vessel. So it actually made a hole in the reactor, not in this one, but in another one. And also, large currents introduce Lorentz forces. In fact, in one of the plasma disruptions that was recorded, the current was so large that it introduced Lorentz forces that literally lifted the entire reactor up by about 10 centimeters. And then it dropped back down, and the seismologic activity of that event was measurable in a nearby village. So that is how large the currents are. That machine is absolutely huge, and it just casually jumped up 10 centimeters. So that is a problem, of course. In the 1980s, the causes and solutions of these problems were identified, and it was theorized that we just need a bigger reactor, better control theory, we need some increasing complexity, for example, cryo-cooling and all that. But that was very, very expensive back then. It's still expensive now, but back then it was unattainable. So work began on advanced tokamaks. And the main principle of those tokamaks is that they are larger, because when it comes to nuclear fusion, size really matters. If you have a large reactor, then your temperatures will be better, your confinement times will be better, and you just have more fusion output. So that was 40 years ago. And in the meantime, we still have done a lot of experiments with JET. It was actually retired 1 year ago, or half a year ago, I think, because it served its purpose. But in 1980, that's when we started to work on our current reactors, so ITER in France. In 1985, there was an agreement to start on ITER, and right now we are still working on ITER because it is very complex to build such a reactor. So that brings us to the state-of-the-art reactors that are currently available for us. So as I said, in 1985, Gorbachev, the last leader of the Soviet Union, contacted President Reagan of the US, and he proposed to work together on a large project to show the commercial availability of nuclear fusion. So the ITER project is a huge project. It's one of the largest projects in the world at this moment. And it is a cooperation of 7 nations. And when I say nation, I include, for example, the EU as one nation. So it's a cooperation of China, the EU, India, Japan, Korea, the Russian Federation, and the US. In 1988, design of the ITER project started. So what do we need, how large do we want it to be, and so on. And in 2005, the decision was made to build ITER in Cadarache, France. Why was it chosen to be in France? Well, first of all, France has a very rich history of nuclear energy. They have a lot of nuclear power plants, so they have a good infrastructure for R&D, for example. Also, France was a strong advocate of the project, and they also provided a lot of funding, so that is also obviously an advantage if you want that reactor in your country, because obviously all the countries wanted the reactor in their country. And France also had a very suitable location to do this, so the decision was made to build the reactor in France. So as I said, the ITER project is a cooperation of a lot of nations. In fact, it represents about 50% of the world population and about 85% of the global domestic product. So it is a huge cooperation in the world. The ITER project is also the largest fusion device that was ever built. If we look at the purple cross-section there, that is a cross-section of jets. So if I cut the donut in half and I just take one side, that is the cross-section. ITER is a lot larger. So again, size matters here. If you have a larger reactor, there's more fusion. And the goal of this reactor was to maintain a power output of 500 megawatts while only requiring an input power of 50 megawatts. So that means that our Q factor is 10. We have never been able to achieve a Q factor higher than 0.76, I think. So this is very ambitious. And as I said, it's the most complicated engineering project probably ever. First of all, the machine is huge. I will go back one slide for a second. There is a person on the down right side. So the machine is one of the largest machines that is ever being built. And also the magnet in the center of the reactor is the largest magnet currently on the planet. Well, if it's built already, I'm not sure actually. Yeah. Of course, the project is also very expensive. It's 18 to 65 billion dollars, so that is a lot. We don't know exactly how much it is because, first of all, it's hard to make that estimation, to make that estimate over the last 30 years. And second, it's not finished yet. A lot can still happen. And now with building materials going up in prices and all that, it's hard to make an accurate prediction of how much it's going to cost in general. The initial budget was 6 billion, by the way. So we have already overshot our budget by quite some margin. All the components of the reactor are also made by different countries. So every country has their own responsibilities with regards to reactor components. That doesn't mean only producing, but also design and research to those components. So that's why it's taking so long to build this reactor. There is also a lot of research still to be done. So usually these components are built in the nation where the research is developed. And then they are transported to France, to the location of the ITER project. These components are massive. And for that reason, France actually built a highway specifically to move those components to the project location, because they are very heavy and just very wide sometimes. Some components are too large to transport, so you need to build them on site. There's nothing you can do about that. But just to show that it is a very complicated endeavor here to get everything in the location. So what exactly is the purpose of ITER? The purpose is, of course, to show nuclear fusion is commercially viable. And it is currently still being built, but we're nearly finished. We hope to start our first plasma experiments in 2025, so that's in 2 years. At this moment, as far as I know, everything is on schedule, so that should be possible. So the first plasma doesn't necessarily mean that we have fusion yet. There are still a lot of tests to be done, but the first fusion operation is planned for 2035. So that is when we have finally, hopefully, a Q factor of 10. Yeah. So when ITER succeeds, we will have finally some concrete proof that it is possible, and then hopefully a lot of investments will start flowing in. That is currently already the case, because we think there will be no more surprises. But of course, we can't know for certain. Maybe in 50 years, someone is giving a presentation that we were still thinking right now that it was 20 years in the future. And then the next step is a demo power plant. So that's a demonstration fusion power plant. The difference with ITER is that it is typically larger, and of course it has a thermal cycle. So we have a very fancy way of making steam, basically, as we always do for some reason. And it is also, for the first time, connected to the grid. ITER is also connected to the grid, but only to draw power from the grid. It can't put power on the grid, because it doesn't have a thermal cycle. But demo will be able to provide power to the grid. Now, demo isn't one specific power plant. It is, in fact, a class of power plants, and every ITER partner has their own design. So the purpose of the demo power plant is to show the viability, not only commercially, but only in an industrial setting, but also in an industrial setting. So such a reactor would actually look quite similar to what we have right now as a nuclear fission reactor. So you still have cooling towers, you still have a thermal cycle. The only thing that's different is you make steam with plasma instead of burning coal, for example. So where are we at right now? We have made a lot of progress over the last 100 years, as you can see on the graph. So initial experiments were very low temperature, very low confinement times, but every 10 years or so, we make a discovery that pushes us in the direction of where we want to go. In fact, ITER will be the first one to produce a power output larger than the power input. And hopefully it will do that within 10 years. So at this moment, ITER is well underway. We're currently building it. It's almost finished. A new record for the Q factor is achieved every year, basically. Not in ITER, of course, because that one isn't built yet, but in Japanese reactors. JET was also still operational, not anymore now, but a lot of advancements were still made. And we really think that this time there are no more surprises. You can't keep discovering problems and instabilities. At some point it has to stop, we hope. So there's at this moment a surge in private investments. There are a lot of private nuclear fusion companies that are being founded every year because, well, people start realizing that this is really the future of energy production. Now, the main concept of ITER was never tested before. There were a lot of different things in ITER compared to JET. So if we look back at the timeline, 1982 was the year that JET was built. 1997, JET achieved the world record for the Q factor, which is 0.67. And then in 2008, JET was upgraded to mimic ITER more, because ITER is made with different materials. It is controlled in a different way. And we wanted to make sure that ITER doesn't also surprise us in a bad way. So the scientists made JET, upgraded JET, so that it's closer to ITER. So that means new wall materials, optimized plasma shapes, diagnostic heating, a lot of things, but nothing really, nothing really new. So when they turned JET on again, new issues. The plasma was not as hot as we expected. The confinement times were a lot lower. But fortunately, those problems were quickly found, and they were also quite quickly resolved. So, as I said, in 1997, JET achieved a world record for nuclear fusion. So that is the main spike there. And last year, in December, we finally have the breakthrough that we've been waiting for 100 years. Because JET was able to maintain a Q factor of 0.33 for about 5 seconds. And if you can do something for 5 seconds, then you can do it for as long as you want, because the timescales of plasmas are very, very short. So if it's stable for 5 seconds, then you can keep it stable forever. So why is the Q factor lower? Because it was not designed to be to break new records. We just wanted to check the improvements that we made, do they behave as expected? If we want a higher Q factor, then we just make the machine bigger, which is exactly what ITER is. So this breakthrough, again, very optimistic, and a lot of investments are flowing in due to this breakthrough. So we are basically in the last sprint of the race here to get to nuclear fusion. But there are still quite some challenges that remain. For example, in the first slide that I showed you that deuterium fuses with tritium. The problem with tritium is that it's very hard to get tritium. At this moment, there is less than 20 kilograms of tritium on the planet, and it has a price of $30,000 per gram. That's insane. You don't want to do an experiment every day that consumes tritium. Also, it's very hard to get new tritium. You can't just get it. You can't just buy it. So that is a problem, because we can't really test our current reactors by burning tritium, because we need it for ITER. And ITER will, of course, have its own tritium source, because if you remember, there is a neutron produced with a nuclear fusion reaction. And tritium is just deuterium plus one neutron. So if you catch that neutron and you let it go through the other fuel, the deuterium, then you make tritium. At this moment, we can't really do that, but ITER will be able to do that. That is also one of the main goals of ITER, by the way, that we can test if that actually works. It's, of course, a very complex aspect of nuclear fusion, and it's a bit too much to explain right now, but that is one of the main critical remaining challenges. Also, plasma instabilities and disruptions, we haven't been able to completely solve them. We're able to mitigate them, but we can't get rid of them indefinitely. So we need to have better control theory, because at this moment, when a disruption occurs, it damages the plasma wall. ITER is designed to have about 2,500 of these disruptions, I think. And when we go over that, then the reactor is unusable. Of course, ITER is not going to be run continuously, so we're not going to get to 2,500 disruptions, hopefully. But it is a problem for actual reactors in the future. So a lot of research is being done in control theory, and we are also making quite some advancements. Of course, material sciences also still needs to improve, because when you look at the JET graph that I showed you, the 5 seconds of nuclear fusion, that's only 5 seconds. And JET doesn't have active cooling. It has inertial cooling. So that means the plasma walls have mass, and they can absorb some heat before breaking down. If you do it for longer than 5 seconds, JET is able to do that. But first of all, the tritium is insanely expensive. Second, the reactor would melt. So that is undesirable if you want to use it in the future, of course. For continuous operation, we have active cooling, which is based on cryo cooling. So that's also a relatively new technology, but the difficulty is to apply it in such a large setting with such large heat flows. And economics is also still a problem at this moment. As I said, ITER is crazy expensive. If you make electricity with that, no one will be able to afford it. But of course, nuclear fusion is still a very emerging technology. Just as with solar panels, the price will drop drastically over the years. And that is exactly what Demo will try to achieve, of course. So I forgot to show this, but this is on the tritium fuel cycle. So that is where we are at right now. And now I want to talk a bit about what we specifically at KU Leuven are doing. We have quite some expertise at KU Leuven on an international level, so I want to quickly highlight what we do. So this is basically like a short commercial for our research group. So we deal with extremely high temperatures in a reactor, so that means that we need to simulate it. We need to know exactly how much heat is deposited into the vessel. We need to know how the plasma behaves. We need to know how the neutrons behave. That is all very difficult to do. And that is what we in our research group are doing. You can kind of compare the heat load that is deposited into the walls of the reactor to a spaceship returning into the atmosphere. Spaceships, I'm not sure, but I don't think they can re-enter the atmosphere too many times because the materials just can't withstand that amount of heat. So plasma etch models and diverter design is essential. The diverter is the lower part there that is specifically designed to handle these heat loads. But that is not the only thing we do. We have a lot of expertise in a lot of different things because they basically all boil down to the same facts or to the same principles. We at the KU Leuven, we are specialized in multi-scale and multi-physics modeling, so that means small scales and large scales combined in one model. Multi-physics, for example, thermal models and hydrodynamics models. So a lot of things come together in our models. Of course, they also need to be efficient. At this moment, the figure on the left is a direct numerical simulation of plasma etch in 2D. And it takes really long to calculate that. In fact, if you want to do a three-dimensional simulation of even a very small part of the reactor, then it will take weeks or months to compute, even on supercomputers. So that is also what we do. We make existing methods more efficient, and we devise new methods to do efficient computation. Shape and topology optimization is also something that we do. So, for example, the second picture there is a heat network in a city used to deposit heat in homes. So, what is the optimal way to design such a network when looking at pipe diameters, locations, and all that? And we also do uncertainty quantification because that is really necessary, especially in plasmas where we don't know a lot. So yeah, that is in principle what we do at the KU Leuven. More specifically for nuclear fusion, KU Leuven, our research group, is one of the leading development teams for simulation software concerning plasma etch modeling. So we need that to see the particle and heat load deposits in the reactor. So the KU Leuven is one of the leading development teams. We make the code, we continue to support the code, and we improve the code constantly. We also have a lot of cooperations in this regard. So we directly work with ITER, we directly work with the Max Planck Institute. So there are a lot of cooperations on an international level. So in conclusion, we do a lot of things at the KU Leuven, and they are very interesting, and we are really at the frontier of nuclear fusion because we have a lot of expertise. And of course, the collaborations don't stop with ITER and Max Planck Institute, for example. We have cooperations all over the world. So if you're interested in nuclear fusion and if you want to really make a difference on a global scale, then I can only recommend that if you haven't chosen your thesis topic already, that you choose it in our research group. Okay, I think that's it. Are there any questions? No, no. ITER will not be able to make commercial power because it's just not designed to do that. The only reason that we want to make ITER is to show that it's possible to maintain a fusion reaction that produces enough energy. Connection to the grid and producing energy is for demo, or proto, which is the successor of demo. The main goal of ITER is show that plasma is very hot, show that nuclear fusion occurs in sufficient amounts, and the tritium breeding cycle. We really need to figure out how to do that. Yeah. Yes. So the news in December last year was on inertial confinement fusion. So that means instead of making a large reactor and heating up the plasma to make fusion, you just have a very small pellet of fuel, like 1 centimeter in diameter maybe, and you bombard it with lasers. So in a very short amount of time, you deposit large energies. The center of the pellet will fuse, and then a lot of energy is released. So what they achieved was really great because that's the first time we had a Q factor of over 1. I think it was about 1.5. But indeed, the lasers were not accounted for. That is something we never do, by the way. We only look at heating and the power that comes out of it. But with inertial confinement fusion, that is kind of an issue because lasers are incredibly inefficient. They have efficiencies of 1% maybe, so you need really a lot of energy to get those lasers going. Lasers are also huge for this purpose. The building that contains these lasers are larger than our campus. It's ridiculous how big it is. But that being said, it was a nice advancement in nuclear fusion. Yeah. At this moment, ITER has a lot of competitive advantage over these techniques because, okay, you have achieved nuclear fusion in one pellet, but you can just take another pellet and turn on the machine again. It needs to be continuous, the power output. So that is still an issue. So while it was a huge leap in that specific field, it's still not going to overtake ITER for the next years. Yes. Well, that is a good question. Well, in principle, we never want all of our energy to come from one source. We want a healthy mix, of course. But nuclear fusion can definitely provide a baseload. And of course, the main cost of nuclear fusion power plants is the capital cost. You need an enormous amount of money to build it. And operation is actually not that expensive. You just need water to fuel it. That's quite okay. And tritium as well. So that's super expensive, but we're trying to breed our own tritium, of course. So nuclear fusion will take a very dominant role if everything works out. But we will still always have other options as well. But I can't give you an exact number of how much of our energy would be produced with fusion. More probably. If yeah, I think so. I think so. When nuclear fusion works, yeah, then it will quickly overtake nuclear fission, I think, because if you try to make a nuclear fission reactor right now, that's also very expensive. That's also 10 to 20 billion dollars. That's almost as expensive as ITER if nothing further goes wrong. So there is not really an incentive to keep doing nuclear fission. Mm-hmm. Yeah. Yeah. Mm-hmm. That is a very good question, because indeed the temperatures in such a reactor are either extremely high in the plasma or extremely low in the surrounding materials. In fact, when ITER becomes operational, it will both be the coldest and the hottest place in our solar system at that time because it's so warm and so cold. So it also has the largest temperature gradient in the solar system. So that is indeed an issue that we need to solve. One way to do that is make use of vacuums to kind of isolate the power. And there is a lot of active cooling involved, so it will require a lot of electricity to keep that stable, but it is possible to do. Yeah. Um, I think if we have a Q factor of 10 for ITER, okay, let's say that the cryo cooling uses a bit more than expected, and our cooling and our Q factor becomes 9 or 8 or even 5. That is still very good. At this moment, we can do 0.67, so it's still a huge improvement. Yeah, I hope that answers your question. Mm-hmm. Yeah. Yeah. The tritium fuel cycle is difficult to do, but it doesn't require a lot of electricity because you just have the reactor and you surround it, use it as a blanket. It's called a tritium breeding blanket. And neutrons will automatically be caught by the deuterium and form tritium. Um, it's not easy to do. It's very difficult to do, in fact, because we have to moderate the neutrons. They go too fast. They would just go straight through the deuterium. So we need to moderate them. Also, for every fusion reaction that you have, you need to make one tritium atom because you will need that tritium atom to make the next fusion reaction occurs. Um, um, so you also need to multiply the neutrons. But of course, you have very fast neutrons, so that is not very difficult to do. But that doesn't really require a lot of electricity. I mean, the physics principles by themselves. But you make a good point that it's all costing a lot of electricity, and that's why the output of ITER is 500 megawatts, and the input is 50 megawatts. That is 50 megawatts is not nothing. That is a lot. But nuclear fusion has such an enormous power output that it's fine. And also, once it's in operation, the operational costs are quite low. So, yes, efficiency is important, but we have some margin. Also, we can just make our reactor bigger. There are already plans to make reactors in China, I think, with a Q factor of 15 or even 25. So if you just make them bigger, the efficiency becomes better automatically.
Thank you all for joining. For all the people that joined us today, thank you. We also have another talk next week. Also, a feedback form will be shared. We'll be happy if you scan the QR code on the top right. No, that's for the. No, it's for the feedback. Yes. The feedback. No, it's this one. Yep, it's this one.